All right.
Okay.
I'd like to introduce our next speaker, who's Per Simonsen, who's the CEO at MSST. And so Per was kind enough to come here all the way from Norway, so very much appreciated. His company, he'll talk to you about what they're doing. But again, they're leveraging these technologies within Intel and, in this case, ARM coprocessors. So we wanted to make sure we got ARM into the mix as well. So again, Per, thank you for coming, and over to you.
Yes, thank you. Yes, so hello, everyone. As Matthew mentioned, I'm the CEO of MSST, and today I'm going to talk to you about the status of erasure coding libraries and what performance improvements that have been achieved on both with software optimizations, but also with the development of new algorithms. So first, I'm going to talk to you a little bit about our company. So it's a quite small company, so it may be that you haven't heard about it before. Then I'm going to take a very brief introduction on erasure coding, and then I'm going to talk a little bit about erasure codes that we have developed. And towards the end, I will compare the performance of our library to some of these alternative libraries. So, the MSST company. We are a startup. It's a spin-off company from the Norwegian University of Science and Technology. It was started in 2015, and it was a result of a research project in algorithm development within network coding, but also algorithms for data storage. This spring, we raised capital, and that was in order to commercialize this C library that we have, but also some plugins for open source storage systems. So the team consists of 6 people, so not a very large team, but it's a very hardcore tech team. We have some professors and PhD, and I myself have a background in both computer science and also some business. And our core competencies in our company is algorithm development and also optimizations. And some of our previous, or some of the team's previous accomplishments are providing the fastest unbroken SHA-3 candidate, which is called the Blue Midnight Wish. And then we also, as far as we know, have optimized an implementation of traditional type of read-Solomon to become the fastest available today. So I'm not going to talk very much about what erasure coding is. I assume most people here know what it is, and also Greg had a good introduction on that. So I'm just going to flip quite fast through these slides. So this is replication, making copies of data. This configuration can tolerate 2 losses before you lose any data. With erasure coding, we take the data and we split it into fragments, and then we add some recovery fragments. And if we add 2 recovery fragments, this configuration will also be able to tolerate 2 losses. And the advantage of erasure coding, you can see that here. With the replication, we have 200% overhead. With erasure coding, we have 50% overhead. And that means that you can store twice as much in your storage system. Like in a real storage system, you will usually use more redundancy fragments than this. So this is a bit simplified example. So in many cases, erasure coding can actually improve the performance of the storage system compared to replication. But there are also some challenges, and these are especially when you recover lost data. And you might see very high network traffic and IOs. And also, when you calculate these redundancy fragments, it can be quite computationally intensive. And at MemScale, we have worked at solving these challenges with erasure coding. And we do have some solutions to each of these. And if you implement this in your storage systems, you may see improved performance. You will also be able to achieve higher levels of cost savings by reducing the overhead. And also it can provide better protection against data loss. So I'm going to go a bit more into detail on a few of these. First we have the reduced network traffic. And when I say recovery traffic, I mean the amount of data that you need to read and transfer over the network in order to recover any lost data. So if you reduce the recovery traffic, you can potentially have faster recovery because you need to move less data in your storage system. And if you have faster recovery, you will also achieve a better protection level for your data because the system recovers faster. And also you can potentially have more network capacity available in your system, which you can use for other purposes. And one of them is that you can potentially start to stretch your erasure coding configurations in order to reduce the overhead even more. So I'm going to show you how erasure coding increases the network traffic. So with replication, if something gets lost, you simply copy the data from one location to another one. With erasure coding, it's a bit more complicated because there are dependencies between the fragments that you stored. And that means that you need to get hold of at least as many fragments as you use data fragments in your erasure coding configuration. And that means that the amount of data that you need to read and transfer to recover a lost drive equals the lost data times how many data fragments you used in your erasure coding configuration. And that's with the normal Reed-Solomon erasure coding. We have developed some algorithms to solve this particular problem. And with these new algorithms, we are able to recover the data with only reading 1/3 of the data that you need to read and transfer with Reed-Solomon erasure coding. And this can significantly improve the recovery mechanisms in your erasure coded system. So I'm going to talk a little bit more about reducing the compute. So at MemScale, we have 3 erasure codes currently in our library. We have the code that reduced the network traffic, and then we have an optimized version of Reed-Solomon. And then we have also made a new code which is optimized for fast compute. And this new code, it has many of the same properties that Reed-Solomon does, so it's MDS. And these compute optimizations that we have done in our library, they are mostly for challenging compute scenarios when you have extremely low latency in your storage system, or you need to have very high throughput, and also for low-end processors, these can be useful. So, since we are an independent company, we do optimize for all types of processors. And currently we have optimized for the Intel processor. We have some ARM optimizations. And we have also started optimizing for AMD. And we can also potentially optimize for other types of processors. So we have done some performance benchmarks and compared the performance of our library to 2 of the other ones on the market. One you have heard about earlier here, it's the Intel ISA library. And then also the J erasure library. Both of those are very good libraries and are commonly used today. So this is the test configuration. It's with 10 data blocks, 4 redundancy blocks, and then a block size of 4 megabytes, which means that the data will not, or the data, it's in memory tests where you read the data from the memory. So we have 1 core, and we measure how much data you are able to encode, excluding the redundancies. So we tested this Reed Solomon and also the MemoScale compute-optimized code. So first out, we have the Intel processor. And for this one, we saw that with the J-Erasure, we were able to get 2 gigabytes per second in encoding speed. With the Intel ISA library, it was about 4 gigabytes per second. And we were able to double that up to 8 gigabytes with a Reed Solomon implementation. And then we also have results for this compute-optimized code, where we are approaching 13 gigabytes per second per core. And then we have got some requests to optimize for the ARM library, ARM processors. And so we did for this ARM A53 processor. And to be fair with ARM, this is a very low-end processor. It's being used in some of the low-end mobile phones. It's quite tiny compared to the Intel processor, and also it costs much less and has much less energy consumption. So, but still, it's interesting to see what is it possible to get done on this one. And here we have 200 gigabytes per second, 200 megabytes per second with the J-Erasure library. With our Reed Solomon implementation, we reached about 500 megabytes. And then with our compute-optimized code, we are at about 1 gigabyte per second. Many of you have probably heard about these new processors that are coming out from ARM, now from AMD. They are based on the Zen architecture. So far, the Ryzen processor has been released, but there is also a server, or the Ryzen processor is the consumer version. There's also a Naples processor coming, and we have so far only gotten hold of a Ryzen processor, and we did some optimization for that, and we thought that we could share the results in case you were also interested in that. So here are the results for the Ryzen. It's a bit over 2 gigabytes for the J-Erasure. With the MemoScale Reed Solomon, we are at 8, and with the compute-optimized code, we are at 13, approaching 14. So we will, of course, also optimize for the Naples processor when that arrives, and I think it's supposed to arrive later this quarter. So, in case someone wants to use this erasure code, we do have a MemoScale C library. It is for integration into storage systems, and it currently supports these 3 erasure codes that I mentioned before. We do provide support and updates, and also quality assurance is very important for us. So we do exhaustive tests of failures and scenarios for these libraries in order to make sure that the libraries are bulletproof. So we also have some plugins for some open source storage systems. Currently we have a Swift plugin and a Ceph plugin. Both of those are for the Reed Solomon code and the compute optimized code. But soon also the Ceph plugin will support the code which reduces the network traffic. We have a beta version of a plugin for Hadoop. It works very well, but currently we need a general plugin architecture to be in place in HDFS before we can release that product. So that's all I have now.
Sugar levels are dropping or something here. Okay.
question. Does your custom code support same configuration as Reed Solomon, meaning all number of data shards, number of parity?
Yeah, it does.
Okay. Which what is the size of Galois field it works for?
I think it's best that my technical guy, which is with me here today, can answer those questions. So if you contact me afterwards, we can discuss that.
Thanks.
Any other questions? Okay, thank you again, Per.